Okay, the next section we want to look at the confidence interval for mu. Let's look at the example 3.3. Suppose that we have a population of the national team which is about to go off for global games, let's say going off to the Olympic Games during the summer. The team is made up of 50 athletes and the skills cover track and field event. And we know that from the population of 50 athletes, 30 of them are males, 20 are females. Then we measure their weight. Okay, so the y variable that we are interested in is how heavy they are. Based on the 50 athletes, we can calculate the true population mean and the true population variance, which are given 7.64 and 73.95. So we collect from the entire 50 athletes, and then we find the mean and we find the variance. If we divided the team into two groups, so each group has a populations of 25, then we sample 5 out of them, and then we can calculate the sample. We want to use the sample to estimate to the population mean. So let's see how good it works using the formula. Collecting 5 athletes' weight, so add them up, divided by 5, and then we found the y bar equals to 66.8. Using the formula we just learned that since we know the true population variance, so we can substitute in here sigma square equals to 73.95, and we have little n, we have population capital N, and we have the little n. So multiply to the finite population correction factor to sigma square of n. We find a true variance of our sample mean, which is 3.511 square. We can say that this sample mean is quite close to the true population mean. The expected value of our y bar is an unbiased estimator of that 67.64. And if we keep repeating collecting sample from the population, we actually could have a distribution of the y bar, right? So with the distribution of the y bar, we can see the variation of our sample mean is 3.511 square. Using that variance, we can take a square root of that variance. It's called the standard error. So under the central limit theorem, it says that if we keep repeating collecting simple random samples of size 5 for, let's say, 1,000 times, we can construct the distribution of the sample mean. From this distribution, we can see that the expected value of our sample mean, which is quite centered in the middle, is very close to the true mean. And we can look at the dispersion of the y bar. Okay, so we can say that by the central limit theorem, that y bar is actually exhibit a normal distribution. That means y bar follow a normal distribution with mean is equal to the population mu, and we can use the variance. The variance, we can either use this value, or if sigma square is not given, we can use our estimated variance of the sample mean, so which is sy squared divided by n multiplied to the finite population correction factor. Okay. What is the use of these? With these, we know that because it's a symmetrical under the normal distribution, so if we can obtain the y bar from a particular sample, we can use the central limit theorem, that is to y bar plus or minus the critical value of a normal distribution multiplied to the standard error. So that gives us a confidence interval. With that, That means if we collect a sample from the population, we calculate the y bar, and we know that y bar plus or minus symmetrically a certain value, we could say we are quite confident that the true mu, or the true population mu, does fall within that range. Okay, so for example, if we are setting our significant level alpha equals to 5%, then we can look up the critical value of 5% divided by 2, because this is two-sided, right? So critical value at 2.5%, so that the critical value, look up the normal distribution table, is 1.96 multiplied to the standard error of the sample mean. So we can say that as a statisticians, we are 95% confident that the true value of mu fall into that range. Okay, so the following text, if you look into that, I'm not going through that in very details, because what it is saying is that if the population size is not large enough, and if our sample size is not large enough, then we could use student t distribution rather than a normal distribution. So that really depends, assuming the sample size is not large enough. So normally n is small, n is less than 40, then you can argue that the sample mean does not follow a standard normal distribution. It actually follows a student t distribution. Then the critical value we should look for is from the t table instead of the normal distribution table. Okay, but I would say that to keep it simple, in this course, we would just assume the sample mean follow a normal distribution. So we would only use the critical value that obtained from the standard normal distribution. Okay, so we can just ignore using the t distribution for the sake of it. Okay, one more example. In a particular sector of industry, a survey was conducted in an attempt to investigate the extent of absenteeism not connected with the illness or official holiday. So that means whether the staff, they are taking they're being absent but not really ill, is not taking the official holiday. So let's look at a random sample of 1,000 workers out of the total workforce of 36,000. So we can see that the population size and the sample size, they are relatively large enough. So we feel comfortable to use the normal distribution. Assume the sample mean follows a normal distribution. And then we ask how many days they have taken off in the previous month. Okay, so number of days off, only we have 451 workers. Taking 1 day off, there are 162 workers. 2 days off, 187 workers, etc., etc. Okay. So we can calculate the average number of days, or we can call it the casual holidays taken by the workers. So we can multiply the frequency of the number of days, multiply to how many workers that's taking that number of days off. Okay, so in this case, we can use the summation of the 0 times 451 plus 1 times 162 plus 2 times 187, etc. And then divided by the total number of workers, we can find that the sample mean is around 1.296. So the on average number of days that the workers are taking a day off is around 1.296. Using our sample, we can calculate the sample variance. Since in this case, we're not given the true values of all of the 36,000 the staff, so we don't know the true variance sigma square. What we can do is to use our sample mean, y bar, plus or minus our critical value, 1.96. If we're assuming 95% confidence interval, then our 1.96 multiply to our standard error. The standard error is the square root of the estimated variance. Okay, so sy square, taking a square root, so we keep it in here, 2.397 divided by n, multiplied to the finite population correction factor. So this is the range. Okay, if we ignore the finite population correction factor, because this number here is very small, very close to 0, our sample size is very irrelevant as compared to the population size, that could be quite close to 1. The confidence interval is about 1.201 to 1.391. Okay. So having that our sample size of 1,000 is good enough that we assume the sample mean y bar follows a standard normal distribution. And we are quite confident to say that on average, the number of days, the true value of mu, actually falls within this range of 1.21 or 1.391 days per worker. Okay.